Welcome. So this is 48P video 1, and this chapter is on fluid mechanics, and it's broken into 4 bits. We're going to talk about pressure, and then we'll talk about a thing called Pascal's principle, which is the basis for hydraulics, and then we'll talk about buoyant forces and Archimedes' principle. We'll be discussing objects that are submerged and objects that are floating. And then in the last bit, we'll talk about fluid dynamics. So this first tape is about pressure. So, what is pressure? Well, pressure is defined as the force per unit area. So, pressure is measured in Pascal, and the force is measured in newtons, and the area is measured in square meters. So a newton per square meter is a Pascal. Pressure equals the force per unit area. The standard unit is the Pascal, where 1 Pascal equals 1 newton per square meter. There are other common units, and these are things like inches of water, millimeters of mercury. And these 2 units actually come from a very practical aspect where when people didn't really understand what pressure was, they could see its effects and they could measure it. And one of the common ways they measured it was they connected, say, a chamber full of high pressure gas to a thing called a U-tube manometer. And the U-tube manometer would swing out of balance, and a column of liquid would be pushed up, and the length of that column of liquid would indicate the pressure. So the inches of water and the millimeters of mercury are 2 very practical ways of just measuring the pressure, not from a fundamental point of view, but from a purely a measurement pragmatic point of view. And then there's the imperial equivalent of our metric system, which is, rather than using newtons per square meter, we can use pounds per square inch. Now, frankly, with the way things are, industries, once they adopt a unit, tend to keep hold of it. So in a typical working life, you will see pressure measured in pounds per square inch when you're dealing, for example, with high pressure gas cylinders. You will see pressure measured in Pascal, or another unit which is very, very common is the torr, named after Torricelli, which is used in pressure systems where they're below atmosphere, very commonly used in instrumentation, and the like. Millimeters of mercury, blood pressure, for example. It's very interesting how these things linger on. Let's look at a practical example. We have a bucket full of water. I'd like to know the pressure at a certain depth. And I can talk about this in terms of the absolute pressure. What is the absolute pressure at a certain depth below the surface of an open container filled with water? Well, I can say the absolute pressure is equal to the atmospheric pressure, because the chamber is open to the atmosphere, plus what's called the gauge pressure. The gauge pressure is the inches of water, the thing you use on the pressure gauge. And the gauge pressure is the density of the fluid times the gravitational field strength times the height of the fluid. So the pressure absolute is P abs, and the pressure ATM is pressure of the atmosphere, and the rho GH is the gauge pressure. And final comment, 1 atmosphere is a tremendous number of pascals. It's 101,000 pascals, basically. So a pascal is, in some ways, a very tiny unit. We tend not to like tiny units, but we have one in this case, coming from the SI system. Let's use this. So let's do a couple of examples. What is the pressure exerted by a right cylinder? Remember, a right cylinder is a cylinder where the wall at the edge is 90 degrees to the base. what is the pressure exerted by a right cylinder that has a radius of 2 meters? So that distance there is 2 meters. And a height of 4 meters. So the height equals 4 meters. And the density is equal to 8 kilogram per meter cubed. I've got to say a comment about densities. There are two types of density. There's what we should call really the mass density, which is usually just called density, and that's in kilograms per cubic meter. And then there is the so-called weight density, which is the newtons per cubic meter. And the weight density is weight times, when the weight density is measured in newtons per cubic meter. So, if we look at this, we say, oh, okay, well, in that case, then my pressure is equal to, well, it's going to be the force exerted per the area, and the force exerted will be the mass times gets me kilograms, and my G gets me newtons, and my stop.
Sorry.
No, it's me.
Okay.
No, I'm. So, bang. So let's do this. We say that our pressure is equal to our force per unit area. And the force is, well, the mass times the gravitational field strength. And the area in this case, because it's a circle, is pi r squared. So if I want to put numbers in, so let's have a look at this problem. Bang! So let's have a look at this problem. We have that our pressure is equal to force per unit area. And I know that my force, well, it's the mass times the gravitational field strength over pi r squared. And well, my mass is going to be my density times my volume times G over pi r squared. And that means my density, my volume will be pi r squared h, base area times the height, times G over pi r squared. Things are beginning to cancel, of course. That pi r squared goes with that pi r squared. And so I end up with my density equals rho GH is the way we normally say it, which is going to be, in this case, is going to be 8 times 10 times the height, and in this case the height is going to be 4 meters, which would be 3/8 of 24, 4/8 of 32, 320 Pascal. 320 Pascal. There. So notice, please, that the radius actually does not matter, because if I widen the radius, I get a bigger area, but I also get more force because I have a bigger volume of this dense material. Let's look at the next one. A barrel is filled with fluid as a density, so the density is equal to 4 kilograms per meter cubed. The barrel is open to the atmosphere. The atmospheric pressure is 80 Pascal. It's a really low pressure, but that's okay. What is the absolute pressure? 3 meters. So this is 3 meters below the surface. And what we say is, we say that the pressure absolute is equal to the pressure atmospheric plus the gauge pressure. And so my pressure absolute is equal to my pressure atmospheric plus rho GH. So my pressure absolute is equal to my atmospheric pressure, which was 80, plus my density, which is 4 kilograms per cubic meter, times G, which is 10, times my H, which is 3 meters. So this is going to be 80 plus 120. So P absolute is equal to 200 Pascal. Now, I could have asked you for the gauge pressure, even though I gave you the atmospheric pressure, and then you'd have had to just ignore the atmospheric pressure. So there's various ways I can rearrange this question so that it's interesting. Let's look at instrumentation for a couple of minutes. There's two basic forms of instrument. There's the so-called open tube or U-tube manometer, and then we have what's called a barometer. The U-tube manometer is basically just literally a U-tube that we fill with some fluid. And normally the level of the fluid is nice and balanced. And then we apply a pressure. In this case, the pressure is above atmospheric. And so the pressure causes the fluid to move downwards until, if you like, the force downwards caused by the pressure is balanced by the force upwards caused by the imbalance in the fluid. This column of fluid is causing a force which balances out the other side. So this is a really useful way of measuring pressure. Actually, we can look at the column of the fluid and it will give us a direct measure of the excess pressure. Excess meaning above this atmospheric pressure. So we call it our test pressure. Our test pressure is equal to our atmospheric pressure, because that's on this side, plus our gauge pressure. So what we called before our absolute pressure underneath the surface of a liquid. Well, if you imagine underneath the surface of the liquid we are here, and the pressure there is going to be the same as the pressure here. So it's the same principle, really. So that's used to some extent. These days we tend to use membranes and capacitors to measure pressures, but you still find this around in some laboratories. The barometer is the next level of this. Truth be said, because the atmospheric pressure is included, the gauge pressure does not directly measure the test pressure. So we can't know the actual test pressure unless we know the atmospheric pressure. And that's a bit of a pain, because different days we have different pressures. So a way around that is to get rid of the atmospheric pressure. And so what we do is we completely fill this tube with a liquid like mercury or water or whatever. And then as we, well, I don't know how to describe this. If I have a tube that's underneath the surface of a liquid and it's filled with the liquid, and then I bring the tube outwards, it will keep the liquid inside it. So the liquid will be dragged up because the liquid, basically the water is being pushed down and the pressure on this side is not great enough to balance it. But at some point I'll get to the stage where I create a surface, and then from then on it doesn't matter how high I go. I'm making a stretchy tube, I know, but there'll be a certain height, and the liquid will not go above that height, because that pressure there, the pressure caused by that fluid, is the same as the atmospheric pressure. So this up here is called a vacuum, and no atmosphere basically. Let me erase this. So that's a vacuum, no atmosphere. So that's how we make it. So it simplifies our math, because what it means is that our test pressure is simply equal to our gauge pressure, which equals rho GH. It's a very nice system. And what tends to happen, frankly, is because this is a great way, because this does not include atmospheric pressure, people tend to use it to measure atmospheric pressure. So now we have our test pressure is P atmosphere. And then we find that this thing here is indicative of the pressure caused by the atmosphere. The pressure here is the same as the pressure there. So let's do some questions on this. So we say an open tube manometer is filled with a fluid that has a density. My density is equal to 6 kilograms per meter cubed. A cylinder of compressed gas is connected to one end of the tube and it causes a height difference. So my H is equal to 4 meters. The atmospheric pressure is P atm is equal to 300 Pascal. And so what is the P test? So P test is equal to P atmosphere plus P gauge. And P test is equal to P atmosphere plus rho GH. And so P test is equal to, well, atmosphere was 300 plus rho GH is going to be, rho is going to be 6 times 10 times 4, which equals 300 plus, and it's going to be 6 4s are 24, 240. So P test is equal to 540 Pascal, 540 Pascal on that one. Sometimes people ask me and they say, why do you bother writing down those equations over and over again? And there's two reasons. One is that I want to remember them, and so the more often I write them down, the more they get into my long-term memory. You don't want things in your short-term memory. It's like doing all the work but getting no benefit from it. You want things in your long-term memory. And so you do it often, if you can, every day. You do a little bit. And by the time you've done it for a couple of weeks, you know it. Because you've done it every day. It's in your long-term memory. Rather than using that same amount of time the night before and you cram it into your short-term memory, and the day after you can't remember any of it. So I always do a little bit of homework regularly. And the second reason I do it is that I don't want to use my mental capacities more than I need to. So by writing things down, I don't have to remember it in my head as I'm doing the problem. I can read it and say, oh yeah, what's P atmosphere? Let's look over here and find it. Oh yeah, what's rho? It's over here and find it. I think when people just put down the numbers, they're really making it hard for themselves. Let's look at this last problem. A barometer is filled with fluid that has a density of 8 kilograms. So let's have a look at our barometer. Our barometer is just slightly different. It's just got a sealed end on this tube. And it's filled with a fluid that has a density of 8 kilograms per meter cubed. The atmospheric pressure causes a 5 meter, so this is 5 meters, column of fluid to stand above the reservoir. What is the atmospheric pressure? So my reservoir is kind of like here. Let me redraw this because I'm actually referring to the other version of this. So here's my reservoir. Let's draw it like that. So here's my reservoir with my atmosphere pushing. And then we have our vacuum up here. And then we have our height there. It's like a U-tube, it's just it doesn't look quite the same. And so we say, oh, well, in that case then P atmosphere, which is basically the same as P test, equals P gauge, which equals rho GH. So P atmosphere is equal to rho, which we said was 8, times G, which is 10, times H, which is 5. So P atmosphere is equal to 5/8 of 40. That's going to be 400 Pascal. So there we have it.